Hi, you. Well, this could be you, or this could be you. You could have a family, and you live somewhere. Well, most probably you live in a house which got rooms, and they have walls and ceiling and floor, and basically they look like a cube, so you cube. And what about thermal comfort? Well, it could be cold outside and it's supposed to be warm on the inside. You got some kind of heating device like a radiator or floor heating, and chances are very high that you're not 100% satisfied with the performance of your heating system. So, the U value is a measure of how much heat is lost through a particular material. The relationship between the type of heating, the U value, and thermal comfort are currently unknown. Almost no research has been done in this area. Smart homes without intelligent heating design are not really smart. The solution to these problems is UCube, which is a research facility for energy efficiency and thermal comfort. Well, it has to do with heating, so I think we need to talk a little bit about heating first. And so we made this simulation, which I'll run here. And unfortunately, it makes this video slightly longer than it should be, but probably it's worth watching it. On the left, you got a convector. It's basically two metal plates with an air gap, surface temperature of about 60 degrees Celsius, and it produces basically hot air. On the right, we have the radiator, which is a metal plate with a surface temperature of 120 degrees Celsius. So when you watch this video, you can see differences between the different heating systems, which is not really surprising, but it's most of the time not considered when rooms are designed. The interaction of the heating design, like what you see here with the building materials, could be quite crucial, but nobody keeps a lot of thinking in these kinds of things. So we don't want to show you here which one is better. We just want to show that different heating designs actually are different. Which brings us to, what does this have to do with thermal comfort? Okay, thermal comfort basically can be represented by this green field in this graph. It's defined by PMV, which stands for predicted mean vote, and basically means there are some factors like air temperature, the air speed, surface temperatures, the relative humidity, and a couple of more things that make thermal comfort. That means it makes a zone where most people feel quite comfortable. And now we have a heating method. Let's call it heating method A. This runs a certain graph like this one and eventually hits the comfort zone somewhere. If we have a different heating method, let's say this one, heating method B, then obviously it's different, so it runs a different graph. It hits, hopefully, the comfort zone somewhere else. Now, if we want to compare different heating systems, we actually have a chance here because we'll have two trigger points where the heating systems hit our defined comfort zone. And that's what we will do in the UCube project. So we need a location. It's in Germany. It is in a city called Griesheim, which is close to Darmstadt, and this is how it looks from above. Let's have a closer look.
So this is where the cubes and the calibration grid will be. And you see there is a nice fence around it, and over there is our container. And in this container, we'll have the computers and the hardware to send all the data collected from the field up to the web page.
Well, there's not too many computers yet, but they'll be there in a couple of weeks. So let's talk about the experimental design. So this is how it'll look in a couple of months. You see big cubes and small cubes. And basically the small cubes we'll call calibration cubes, and the big cubes are just the cubes. And let's talk about what we measure where. So this is the same picture, just black and white. And you see, there are two things we'll have to concentrate. The first thing is a calibrated microclimate, because we need to know the climate surrounding the big cubes. And in the big cubes, we basically want to measure the effective U value, which is a measure of the energy efficiency. So for the calibrated microclimate, we'll have 80 weather stations. We'll have 60 of those little calibration cubes. We'll have pulse wave modulation power control. We'll have PID comfort control. We'll have Arduino Pi controllers. And by that, we'll be able to do four-dimensional data acquisition. For the effective U value, we'll start with 2 test cubes that are currently running in the cellar of the school because of the weather. We'll have 8 massive wood cubes be erected in September. We'll have 2 timber frame cubes. We'll have at least 4 different heating systems in every single cube. We'll measure thermal comfort according to the DIN 7730, and by that we'll be able to do energy efficiency measurements. Basically, we'll find the U value, the real effective U value of the materials concerned. So let's have a look at those calibration grid masts, because this is why we are running this crowdfunding mission, because we need 20 of those, because every big cubes should be surrounded by 4 of those masts, and so we need 20 foundations as well, and this makes 20 times 2,000 euro, which is really a lot, and so we need help. So what we do is this: the microcalibration basically is a grid of data that can be acquired surrounding the big cubes, which delivers kind of a matrix, and it has 60 times air temperature, 60 times air speed, 60 times wind direction, 60 times relative humidity, 60 times air pressure, and 60 times heating power consumption of the calibration cubes, which gives us a quite good idea of what is actually happening surrounding our cubes. And additionally, we have 20 rain sensors and 20 times solar insulation to find out like what is going on with the sun right now. So all these data then go to our webpage, and you will be able to see what's happening in which cube and how the weather currently is interacting with the cubes. So for that, we have some partners, which is basically a lot of universities and institutions that help us and send students over, and actually students from the school and students from the universities together do research, from practicals to bachelor and master to PhD works. So it's a huge thing that has never been done by a school like this. So that means it has a quite interesting cooperation. Like schools and the industry and universities are actually doing something together, run and operated by the school, with the help of the industry and the university, and we'll deal with certain aspects of physics and engineering and even architecture. So now I need to finish this quite long video with thank you very much, and I hope you can help us with this really, really unique, fantastic project. Thank you very much.